Today's topic is all about varying currents. Resistance, inductance, and capacitance. Before we understand what exactly the varying currents are called as a transient current, let us understand what is resistance, what is inductance, and what is capacitance. Normally, resistance are components which opposes the flow of current, which is in steady or which are in varying or which are in alternating currents. Steady currents are what? It is nothing but a direct current. Unidirectional current are called as a direct current. What about varying currents? Varying currents are the currents which are also called as a transient current. So transient currents are the current which exists for very short interval of time. So the currents which exist for very short interval of time are called as varying currents. So these resistors opposes the flow of current. It can be steady, it can be varying, or it can be alternating. What is capacitor? Let us understand the capacitor. It has the ability to store an electrical charges. As well, it can block the package of DC, and it opposes the charge of voltage in the current. It means an ability to store an electrical energy can be called as a capacitor, which blocks the DC and allows the AC to pass through it. The last component called inductance. By this circuit, you can understand this have the ability to store an electrical energy, and this is keep resisting always. It is not having anything. It have an excess of energy which is stored as in the form of electrical energy. Inductance. Inductors also opposes those current which are either varying or alternating. So again, if you understand all the three components called resistance, inductance, and capacitance, all the three components opposes the flow of current in the circuit with a certain conditions at certain stages. But why we use all these components? Then what is the use of components when we say that it is opposing the flow of current in the circuit? Let us understand. So with this, other than this resistance, we will be also studying about reactance. Nothing but resistance produced due to inductance or capacitance called reactance. And if we add this particular resistance and reactance, then that can be called as an impedance. It means the joint effect of resistance and reactance is called as an impedance. So all these three components we will be studying with a different combination, if at all. What will happen on what will be the nature of the circuit if the DC source is applied to different combination of the circuits. As we said that this is notches, the inductance is notches, only a single pi it is selecting, and this is nothing but a capacitance can be called as a band pass. So what is that? A filter can also serve to select or eliminate a narrow band of frequencies. Can you see this? Can you see this? Examples are radio and parental control channel eliminator circuits. So here it is selecting, or here we can say it is eliminating a narrow band of frequencies. So this can be called as a notch, and this can be called as a band pass. Overview of this video. will be, the first point will be EMF, understanding the EMF and terminal voltage, resistors in series and in parallel, Kirchhoff's law, EMF in series and in parallel, charging a battery, circuits containing capacitors in series and in parallel, then all the different combinations like LR. So in the case of LR, we will study growth and decay of current. Then the next combination will be CR, where we will study growth and decay of charge. LC, growth and decay of charge. And here in the case of LC combinations, we will take resistance, we will allow the condenser to fully charge through the resistor and discharge through the inductance. We will first allow the condenser to get it into its fully charged value, and we will disconnect it and we will discharge this condenser through the inductance. So then we will understand how the LC circuit acts as a simple harmonic oscillator. Then the last will be natural response of LCR circuit, which is in series as well as parallel. So let us understand the basic of this first. See, any conductor will be having a plenty of free electrons. So these free electrons will not flow unless and until an external source is connected to this particular conductor. So how we will define the electric current? When we connect an external source to that particular conductor, all the free electrons which are present on the conductor, which were in a random motion, will align into a straight line and flows towards the positive polarity of the battery. So the rate of flow of charges, all the electrons, the rate of flow of charges are defined as an electric current. So electric current needs a battery or generator to produce current. These are called sources of EMF. Battery is a nearly constant voltage source, but does have a small internal resistance which reduces the actual voltage from the ideal EMF. So the source which we are connecting will have its own internal resistance, and that will be of value of a small resistance, which is called as an internal resistance with a value of small r. So if you measure the potential difference across that particular conductor, let us assume it is an A and B, then the potential difference across that particular conductor will be, this is a total EMF source which we have applied to a circuit, minus I, which is flowing through, I as a current flowing in the circuit, into a small resistance value. So this will give the total potential difference in the circuit. VAB should be equal to E minus IR. This resistance behaves as though it were in series with the EMF. See, if you just see into this particular diagram, this is a point A and B, plus and minus. This is the EMF which we have applied. So, though physically we cannot see the resistance, this is an internal resistance, but we can see that this particular source is in series with this particular internal resistor. So this is a terminal voltage, called as a terminal voltage, or the potential difference across this conductor. So that is called as an VP. So what will happen to this particular resistance if they are connected in series or parallel? A series connection has a single path from the battery, though each circuit element in turn, then back to the battery. It means the polarity of this particular source EMF is connected to one terminal of the resistance, the other terminal is connected to the other terminal of the resistance, and then this terminal of the resistance, the out will be connected to the one terminal of resistance. Then the last resistance which we have taken, the terminal of this particular last resistance will close the circuit. So this is how the connections is given when the resistors are in series. And here we can measure, this is the total EMF as a voltage, we measured it as a capital V, and the voltage across R1 is we have taken as a V1, R2 as a V2, R3 as a V3, and I is the current flowing in the circuit. So I will always flows from higher potential to lower potential. It means it will flow from positive to negative. This direction of the conventional current is always in reverse with the direction of flow of electrons in the circuit. So how we will calculate? Suppose we say here as a V is a total source voltage is equal to, should be equal to V1 plus V2 plus V3. So what is V1? Here we can understand V1 is nothing but the I is the current flowing in through each of the resistance. So this comes like I into R1 plus I into R2 plus I into R3, or simply we can say that I into R1 plus R2 plus R3. So what will be the equivalent of resistance? If the resistors are connected in series, then the equivalent of all the resistance should be equal to R equivalent should be equal to R1 plus R2 plus R3. Now what will happen the same resistance when they are connected in a parallel? See, here we have a drawback when the resistors are connected in series. The same voltage will be divided across each of the resistors. The same voltage will get dropped across the each of the resistors. But whereas in the case of parallel connection, so these are the connections which we have given in the parallel. Say this is R1, R2, R3. All the three resistors are in parallel with the EMF E. Here we say that the current is I because of the EMF E, and this we can say that the node or junction. And here the current capital I is split into three branches. These are the three branches. This is one branch, second branch, and third branch. So we have labeled each of the branches have I1, I2, and I3 respectively, and which is through R1, R2, R3. This is the equivalent. If we take the resistance in a parallel, then the equivalent resistance we can measure in this, we can construct in a single resistance, saying that this is the equivalent resistance of R1 and R2 and R3 when they are connected in parallel, and this is the EMF source which we have given. So if you take a practical example, here instead of resistance we have taken a bulb which are connected in a parallel. So at domestic purpose or at any of the electric appliances, we prefer to have the connections in parallel, because if any of the fuse here, any of the bulb get fused, even though the current will flow from this particular bulb, and which will make a close with respect to this particular source, and we can see that this bulb and the last bulb will still be in a on stage. Whereas in the case of series, if any of the bulb goes off or lose connections, or the bulb itself have become a fuse state, then the current will not pass to the second connected bulb. So we don't prefer any connections in series. We always prefer the connections should be in parallel. So what is according to Ohm's law? Ohm's law is nothing but the potential difference across conductor should be equal to the product of resistance and current flowing through it. Isn't it? So V is equal to IR, or we can say that what is the I in the circuit? I should be equal to V by the equivalent of all the resistors. And we can say that I, because the main current is split into three branches, we can say that I is equal to I1 plus I2 plus I3. And this I is nothing but V divided by R equivalent. So what is I1? I1 will be should be equal to V by R1. I2 should be equal to V by R2, and I3 should be equal to V by R2. So it means the equivalent of this particular resistance which are connected in parallel, 1 by R equivalent should be equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is what you can see. The reciprocal of equivalent resistance is given by this particular equation. This is the analogy using the water, which can visualize how the parallel circuits are. So this you can see that two equal parallel lines can be called as used to visualize a parallel circuits which will never intersect to each other. Now, suppose you have two sources in the circuit. Ohm's law have a certain drawback. Ohm's law is only applicable when there is a one source in the circuit. So according to the Ohm's law, V is equal to IR, and we can find out the other two parameters, if two of the parameters are given in the circuit. But Ohm's law is not applicable in a network kind of a circuit. In a linear network kind of a circuit, Ohm's law cannot be applied. So here you can see that here you have a two sources. So more than two sources, then the circuit can be called as a network circuit. So here in this is called as a mesh. This is another mesh. This points A and D can be called as a nodes or junction. So here we have a two sources. Here E1 is equal to, we have a value of 80 volt, and E2 is equal to value of 45 volt. And here this is internal resistance of this particular E1 source EMF as in 1 ohm. This is again an internal resistance of this particular EMF E2 of 1 ohm. And we have a three resistance here, 40 ohm, 30 ohm and 20 ohm. So here we cannot find out to find the value of, we cannot apply the Ohm's law to find out the value of current in the each branches like I1 and I2 and so forth. So for that we need a Kirchhoff's law. So to overcome the Ohm's law, through using a Kirchhoff's law, we can find out the current in the each branches. So for this particular mesh kind of a network kind of a circuit, we use a Kirchhoff's law. So we have a two laws. First is called as a Kirchhoff's first law, and second law can be called as a junction law or a loop law. So what is junction law? The sum of currents entering a junction equals the sum of the currents leaving it. It means the summation of all the currents at a junction is equal to 0. If we say that this particular A point is a junction and this current is leaving away from the junction, and this current is also I2 is in the opposite direction, so both the currents are leaving away from the junction. It means minus I1 minus I2 is equal to 0, or we can say that I1 plus I2 is equal to 0. So summation of all the currents here, sorry, so summation of all the currents at a junction is equal to 0 is nothing but a junction law. What is loop law? The sum of changes in potential around a closed loop is equal to 0. It means summation of product of current and resistance should be equal to 0. So here we have taken a Example with this particular circuit, which is having an EMF of 12 voltage, and these two resistors are connected in series. So we can understand through this particular diagram that this we have labeled as an A point, this is B point, this is C, and this is D, and this is E. So here, if you understand, 12 is the maximum voltage. So from D to E, D to E, see, you can see that from D to E, it is rising from 0 voltage to a maximum of 12 voltage, D to E. Can you see here? From E to A, it will be a maximum voltage of 12. See here, this is E to A. And again, from A to B, you have a resistance in between that. So according to this particular 4 ohm value, there will be a voltage drop. So V is equal to I into R. So we have to multiply the value of resistance so that we will get a potential difference across this resistance, or we can say between the point A and B. And again, between B and C, again it is the potential difference across this particular resistance whose value is 290 ohm. So you can understand here it is decreasing and decreasing, and again from its C to D there will be a 0 voltage in the circuit. So what is the points to be followed to apply a Kirchhoff's law is, first label each current in the each branch, identify unknowns, apply junction and loop rules. You will need as many independent equations as there are unknowns. Solve the equation, being careful with the signs. When we have to take minus and when we have to take plus, that you have to consider it. Now, if we have a EMF which are in series, EMF is in series in the same direction. Total voltage is the sum of the separate voltages. So we can take that the total voltage should be equal to, here 1.5 plus 1.5 is nothing but 3 voltage. Here we have connected, see, the positive of the battery, this is an internal resistance, we can neglect over here. So the positive of the battery is connected to the negative, and again this positive is connected to the negative. Okay? So this EMF series, which is in the same direction. So what will happen if they are connected in an opposite direction? EMF is in series opposite direction. What will be the total voltage? Total voltage is the difference, but the lower voltage battery is charged. So difference between these two, 20 voltage and 12 voltage, will be 8 voltage. So the total voltage in the circuit will be the difference of these two particular EMFs. And the voltage, the lower voltage, this is the lower voltage battery, which will be getting charged because this have the higher value. So the effective EMF in the circuit will be 8 voltage. At the same time, the lower voltage battery will be charged. Now what will happen if they are connected in parallel? So EMFs in parallel only make sense if the voltages are the same. Both the voltage which we are applying in the circuit should have the same value. This arrangement can produce more current than a single EMF. So if we want to increase the value of current in the circuit, we can have multiple EMFs, and that too that should be connected in parallel, which should be again having the same value. Let's talk about the condenser. So capacitor in parallel have the same voltage across each one. If you measure the voltage across each condenser, each capacitor, then it will be same. So V is equal to, suppose we say VAB, the potential difference across AB. So across this particular condenser C1, or across particular condenser C2, or across particular condenser C3, the potential difference will be same when C1, C2 and C3 are connected in parallel. So in this case, the total capacitance is, what is Q? Q is the charge. So charge should be equal to CV. C is nothing but equivalent of all the capacitors which are connected in parallel. So here you can say that C equivalent to B should be equal to C1 B plus C2 V plus C3V, or we can say that C1 plus C2 plus C3 into V. It means the condenser, when they are connected in parallel, then the total equivalent condenser value should be equal to C1 plus C2 plus C3. Similarly, if the condensers are connected in series, so this we have taken C1, C2 and C3. Here, the voltage will not be same across each condenser. So this voltage across this condenser will be labeled as an VA, or here VB, or here VC. Okay? And as Q is equal to CV, we can write V is equal to Q by, it is an equivalent capacitor value. So Q by C1 plus Q by C2 plus Q by C3. If you take Q as in common, it will come as in 1 by C1 plus 1 by C2 plus 1 by C3. It means whenever the capacitors are connected in series, the equivalent capacitor value should be equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is all about the resistance and capacitors, as well as the EMF when they are connected in series and parallel, and what is the drawback of Ohm's law, and how the Kirchhoff's law should be applied into a network kind of circuit. Let us understand inductors in a circuit. So inductors are nothing but what? Circuit element with self-inductance, ideally, which will have a zero resistance. As we said that inductor opposes those currents which are either varying or alternating. It means a back EMF will be set up in the inductance due to electromagnetic induction, and this causes a reduction in the current. So that's the reason we say that inductor opposes a flow of current in the circuit. It is nothing but a wire which is into the coil form. So this is a symbol, and here we have taken a source EMF, a resistance in series with an inductor, and we have a switch where we can make a circuit into on or off stage. So how it work actually? Initially, start with no current in the circuit. When the battery is connected, the inductor is resistance to flow of the current. Gradually, the current increases to the fixed value of what is the maximum voltage in the circuit will be V0. So V0 by R will be the maximum current which is flowing through the resistance, isn't it? So gradually, the current increases to the fixed value V0 by R, meaning that the voltage across the inductor goes to zero. In reality, the inductor has a finite resistance. It's a long wire, so it will then be more like a pair of series resistance. As I told you, it is nothing but a single long wire which we have made into a coil form. So that is nothing but it is called as an inductor. And here the potential difference, if you find out the potential difference across inductance, it will be L di by dt. How it comes? Actually, whenever the current passes through the inductor, a varying magnetic field will be produced around this particular coil. It means the total or the magnetic flux is directly proportional to the current flowing in the circuit. So we can say that phi, if at all we say phi is a magnetic flux, so phi is proportional to I, or we can say that phi is equal to Li. L is nothing but a inductance, a self-inductance. So that's the reason, or according to the Faraday's electromagnetic induction, the total EMF is equal to the rate of flow of the magnetic flux, negative rate of flow of magnetic flux. It means EMF was equal to minus d phi by dt. And we said that the phi is nothing but Li, because the magnetic flux is proportional to I. It means magnetic flux is equal to Li. So d phi by dt can be written as minus L di by dt. So that is how we come it as, the potential difference across this particular inductance is equal to L di by dt. And because it opposes this particular voltage, it can be written as minus L di by dt. So in the form of Maxwell's equation, we can write this as E dot ds is equal to minus d phi b by dt. It is a magnetic flux. So E dot integration of E dot ds is equal to minus d phi by dt. So we can modify the Kirchhoff's law according to this. So Kirchhoff's law is nothing but what? It can be a summation of all the current, all the voltages, isn't it? So summation of all the voltage is equal to minus of integration of E dot ds. And according to the Faraday's law, we get it as an E dot ds is nothing but equal to phi dB phi b by dt. Or we can say that summation of V minus d phi b by dt is equal to 0. So if all inductance is localized in inductors, then our problem goes away. We just have the summation of V should be equal to minus L di by dt, because we have found out how we can write the d phi by dt is equal to here is equal to L di by dt. So this is how we get an equation saying that summation of V is equal minus L di by dt is equal to 0. But EMF generated by an inductor is not a voltage drop across the inductor. Okay, so EMF, because this, if you see this circuit, a resistance inductance, and we have switch on the switch, and this is the source as an E. So the total E in the circuit, or E should be equal to, because the potential difference or the voltage produced because of the inductance is opposing this voltage. So this we can say that E is equal to minus L di by dt. Or integration of E dot ds is equal to 0. Because resistance is 0, E must be 0. Non-ideal inductor, not only L but also some R. So as we were saying that the inductance opposes, it means inductance will have its own internal resistance, right? Like EMF have its own internal resistance, and it will be treated as in series with the EMF. So internal resistance is normally of the EMF is denoted by a small r. So non-ideal inductor is nothing but which will have its which will have its resistance values also. So it means it is in series with the inductance. So here we can see that this is an inductance and this is a resistance which is produced because it is opposing the growth of current in the circuit, isn't it? So this inductance, this resistance can be called as a reactance, because this resistance is produced due to an inductance. So the resistance produced due to the inductance is called inductive reactance. Now if somebody asks what is the total EMF in the circuit, then the E should be equal to, because it is opposing the growth of the voltage and current, it should be minus L di by dt as well as minus IR according to Ohm's law. So this will give the total EMF in the circuit. It is opposing, so E should be equal to minus L di by dt and plus IR. So it is opposing, so it is minus IR. How the sign conventions are taken for the inductor? So moving across an inductor in the direction of current contributes E is equal to minus L di by dt. Now if you see this from point A to B, So from point A to B, here you can see that circulate from A to B in direction of current. How the direction is? The direction is from A to B. Then the EMF across this particular inductance should be equal to minus LdI by dt. Now moving across an inductor opposite the direction of the current. This is EMF produced in opposite direction to the current, then the EMF should be given as plus LdI by dt. So these are the sign conventions when we have to take as a minus and when we have to take as a plus. Now, so far we have very clearly understood how and what are the role of resistance as well as what is the role of inductor in this circuit. Let us combine these two particular components, L and R.